Okay, so today we're going to go over chip select memory, which is going to be using smaller memory chips and a module level decoder to build a larger memory. So we're first going to go over an example, and then we're going to do an example problem. So in our example, we have memory chips that are 2K by 1 byte. So the address space is going to be 2K. And then the addressability is going to be 1 byte. And then we want to put those chips together to make a memory that's going to be 8K by 2 bytes. So on this side here, you can actually see how that's going to be done. The main part is that we have the address right here that comes in, and then it gets split off into 2 parts. So part of the address, usually the larger portion of the address, goes into every chip. And then the other part of the address, usually the top few bits, go into the larger module level decoder that you can call like the chip select decoder. So how this is going to work is that the top parts of the address go into this decoder, and then it will essentially turn on and off certain rows in the memory, and then after that you would do like reading or writing. So in order to get an address space of 8K, which is what we wanted over here, we have to make 4 rows of the chips so that we can access 2K different locations here, 2K different locations here, 2K different locations here, and 2K here, totaling for 8K. To get the addressability of 2 bytes, you need to add another column. So how this is going to work is if we put in an address like 0, 0, 0, 0, 0. So all zeros, so the first address, and that's 13 bits, yeah. So how this is going to work is the first 2 bits on this address, bits 12 and 11, are going to go right here into the decoder. And then the decoder is going to decode that to the first row of chips. So it will select this one. Well, let's just say it'll select 0, 0, 0, 1, 1, 0, and 1, 1. So it will turn on this row for reading, and then it will turn the rest of the rows off. So once this row is turned on for like reading or writing, then the other 11 bits of the address are going to go here onto decoders on the smaller chips to select one location out of the 2K locations that are on here. Since we're reading from this whole row at once, we'll be reading or writing to 1 byte of data here, and also 1 byte of data here. So that's what gives us the addressability in total of 2 bytes. So again, because we're accessing this as 1 location, that makes it like as 1 word. So we get 2 bytes there. And then here, because we're giving ourselves 4 rows of these 2K chips, we get an address space of 8K. Okay, so now we're going to do an actual example of how we can build a memory like this in a given problem. So if we have a problem that's giving us smaller chips that are 4K by 4 bits, so the address space is going to be 4K and the addressability is 4 bits. And then we're asked to take those and put those together and make a larger memory that is 16K by 4 bits. We can start by drawing up a similar diagram to what we had before with the larger module level decoder, and then putting chips here. So each of these chips, again, is going to have 4K by 4 bit, or sorry, it's going to be 4K by 4 bits. So if we want to figure out what portion of the address goes into the chip select decoder and what portion just goes into all the chips, we can think of first how many rows that we're going to need in our memory. So again, if the address space is 4K on the little chips and we want it to be 16K on the bigger chips, we're going to need 4 rows. So if we have 4 rows, we'll get a total of 16K locations. So the address space here is going to be 16K. So if we have 4 rows in our memory, our decoder is going to have 4 outputs. So remember for a decoder, if a decoder has n inputs, it's going to have 2 to the n outputs. So in this case, our 2 to the n is just 4, so we're going to have 2 inputs to the decoder over here. So how we can figure out how many bits that we need for the full address then is we can look at the rest of the bits that go into each chip. So because each chip has 4K locations on it, this address part right here has to select one of these 4K locations on here. So again, if we have 4K locations, we would need 2 to the 2 and 2 to the 10, so 12 bits to differentiate between 4K locations. So 2 to the 2 is just 4, and then 2 to the 10 is K. So we have 12 bits going into each chip, and then 2 bits that go into the larger chip select decoder. So in total, that's going to be 14 bits, so our address is going to be from 13 down to 0, with the top 2 bits going into the chip select decoder and the other 12 bits going into each chip.